Hello, 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 hello. Today we are going to discuss conservation of energy. Conservation of energy. We are going to go through a few physical examples where we can actually discuss conservation of energy. We are going to start with a falling ball. A falling ball. Let's discuss the physics or the energy transformations of a ball falling from rest. Okay, so I'm going to have my ball here, and then that's the initial position. I'll have potential energy and kinetic energy here. Here I'll have the sum of potential energy plus kinetic energy. These ones I have to complete. And I'm going to consider a few positions. So I'm going to consider this position. There'll be this position, the middle position, and then somewhere here in the middle, and somewhere in the middle here. Then I will start by giving you the potential energy. Initially is 20 joules. And since the ball is starting from rest, the kinetic energy will be 0. So I'll put a 0 here. The total will be 20 plus 0. That will be 20 joules of energy. Now, I would like to consider, let me first of all do the ground. So the ground is here. That's my ground. And I would like you to consider what would be the potential energy at the ground. Well, as you may guess, the potential energy at the ground usually has to be 0 because the height there is 0. Okay, so 0 here. That will be 0 potential energy. And the kinetic energy has to be, you can guess, you can try to think about it. The kinetic energy has to be what? Well, the kinetic energy there, since you have lost all the potential energy, the kinetic energy has to be 20. So 20, so that the total should be 20 here. On the middle, somewhere on the middle, as you can guess, is halfway down, somewhere on the middle there. The ball will have potential energy of 10. So put 10 here, and kinetic energy has to be 10 as well. So when we add the two, the answer has to be 20 joules. And somewhere here, that's just after the first position, as you can guess, is halfway between 10 and 20. The potential energy should be 15. And the kinetic energy has to be between 0 and 10. That will be 5. So 5. So when we add 15 and 5, we get total energy as 20. So always 20. And somewhere here, when the ball is right here, we see that it's between 0 and 10. So we should have 5 joules of any potential energy. And the kinetic energy has to be between 10 and 20. So that will be 15 joules of kinetic energy. And the result, the sum has to be still 20 joules. As you can see here, what we are having is that we are allowing the ball to fall from rest, and we ignore air resistance. So remember, we assume that we ignore, this happens when we ignore air resistance. We are going to see later the effect of accounting for air resistance as the object is falling. Right now, we ignore air resistance, and numbers will tell us that this will be the case. One thing you should notice here is that the potential energy here is actually decreasing, whilst the kinetic energy is increasing. You can see that the potential energy is decreasing, whilst the kinetic energy is increasing, but the total energy remains the same. It remains the same, 20, 20, 20. Let's look at another example where we have energy transformations as well. And this example will be pushing, allowing the box to drop through an inclined plane from rest. So I'm talking about this one. Use straight marker here. So we have inclined plane there. Okay. This is an example whereby a crate will be falling down an inclined plane. So we have our crate right there, and we are going to allow it to fall through some height all the way here. We are going to start by saying that the potential energy here is 1000 joules. So 1000 joules, and the kinetic energy is at 0. In other words, we start from rest. Now we are assuming that the surface is frictionless. The surface here is frictionless. I don't know where I should write, maybe here. Surface is frictionless, and also we can ignore air resistance as the grade is falling down. Surface is frictionless, and we ignore also air resistance. Ignore air resistance. Now we are going to ask the same questions. We start by what will be the potential energy midway here. The potential energy midway has to be, because it's half the trip, has to be 500. That will be 500 joules here, and kinetic energy has to be 500 as well, 500 joules. Now you may want to know what will be the potential energy and kinetic energy somewhere here. As you can guess, the potential energy here, let me erase this one. The potential energy midway here has to be 750 joules, and kinetic energy has to be 250 joules of energy, 250 joules. All right, so we have lost some potential energy and we have gained kinetic energy. Now what about here, midway between this position and this position? What about here? What will be the kinetic and potential energy here? Okay, so here we are going to have our potential energy as well. Well, it might be maybe nice to first of all deal with this position. And this position tells us potential energy has to be 0. There's no height, and kinetic energy will be 1000 joules. It will be 1000 because we have lost all the potential energy. Now the energy is in form of kinetic energy, and there's no air resistance and there's no surface friction. Now we can come back to this box then, this position. This position, the potential energy has to be halfway between this and 0. So the halfway will be 250 joules, and kinetic energy has to increase between 500 and this 1000. As we increase the kinetic energy, that will be 750 joules of energy. If you look carefully, if we try to add up the two, every position like here, the total energy is the same. 1000 plus 0 is 1000 joules. If you add this plus that, you get 1000 joules of energy. If you add 500 plus 500, you get 1000 joules of energy. If you add 250 plus 750, you get 1000 joules of energy. Likewise, if you add 0 and 1000, you get 1000 joules of energy. So the total energy at each and every position is the same. Again, we are going to see the effect of surface friction and air resistance on this kind of analysis later towards the end of the class. I have another example. This other example relates to a roller coaster. So here's a roller coaster here, goes down, goes down, then it goes like this. somewhere there. Let me try my best to do a good job. Roller coaster. Oh, like that. Well, I tried. So my roller coaster is like that, and I'll draw it here. That's my roller coaster here. Roller coaster, and it's gonna go down the slope, but I'm going to start from kinetic energy of 0, but potential energy I'll give it, for example, 30,000 joules. So 30,000 joules, and I'm going to start at rest. So energy of motion is 0 joules. Now I would like to think about what would be the potential energy right here. What would be the potential energy and what would be the kinetic energy at this point. Let's label the points like this. This is A, and this is point is B, and this point is C, and this point is D. So the potential energy at point D, since this looks like our reference line, remember, we can choose our reference line ourselves. So this is a reference line. Potential energy has to be 0. That's where we can start talking about potential energy. The height is 0 at that point, so potential energy is 0 joules. And kinetic energy must be all of it, because we have lost all the potential energy at that point. When the roller coaster is at point D, we have lost all the potential energy. Therefore, it has to be kinetic energy, which is 30,000 joules of kinetic energy. Now, if I give you at point B, I just want to give you the results at point B. Let's assume that at point B, I tell you that potential energy, just making up a number, roughly speaking. At point B, let's say I tell you that potential energy is 6,000 joules. What can you say about the kinetic energy? Well, as you have seen, if we ignore air resistance and friction on the surface, we have noticed that the sum of potential energy and kinetic energy remains the same. In this case, we can find kinetic energy by subtracting the 30,000 joules minus 6,000 joules. So here we should end up with 24,000 joules, so that the sum of the two should give us the total energy that we had here, the total energy that we had right here. So 24,000 joules makes sense, because 24,000 plus 6,000 is equal to 30,000 joules. Now let's assume we know the kinetic energy at point C. Let's say I tell you that at point C, the kinetic energy is 15,000 joules. What can you say about the potential energy? Think about it. What can you say about the potential energy at that point? Well, if you realize that the sum of potential energy and kinetic energy must be 30,000 at each and every point, you can say that this must be 15,000 joules of energy. All right. So here we have our third example. We are moving on to another example, and this example is an example of a pendulum. But before that, I want to remind you that our assumption here is no friction, surface friction, and no air resistance. Again, we are trying to emphasize the importance of making these assumptions. Again, the solution or the reasoning behind all this will be explained at the very end of the discussion. Okay, let's move on to the pendulum. The pendulum is just a string and a bulb that you can tie, and you can displace it to one side. So this is my mass of the bulb. I can allow the pendulum to swing. It will be found on different positions. For example, my pendulum would be here, that's at equilibrium, but it will be moving. because I displaced it to this level here, at this point, it will have some velocity moving towards the right, and it can go to maximum height all the way here, right here. And it's also possible to find my pendulum in between the equilibrium point and the maximum point here. And also it is possible to find my pendulum somewhere in between the maximum and equilibrium position to the right. All right, so we want to do the same thing, ignore friction at the point of contact here and ignore air resistance that can affect the mass as it is moving around. If we ignore those, we can do the same analysis. So I'm going to start by telling you that the reference line is this one. This is the reference line. In other words, that's the height there can be considered to be 0, so that my potential energy here is with respect to this reference line that I have drawn right here. So the potential energy I would like to give you, because I can measure it by multiplying the mass times the height times g. Let's say I tell you that the potential energy is 4 joules here. What will you say about the kinetic energy? Well, at this point, that's the highest point, the velocity or the speed is 0. The ball is about to return back. So momentarily, the speed is 0, and therefore there is no kinetic energy here. Likewise, on this position, we'll have the same situation whereby the potential energy is 4 joules and the kinetic energy is 0 joules. Same discussion. But what will be the situation right here? Here, we are going to have potential energy equal to 0 because there's no height. Our reference line is right there, 0 potential energy, but the kinetic energy will be all of it, because we need the sum to always equal the same. The sum has to always equal to 4 joules. So the kinetic energy has to be 4 here. That means the ball has no potential energy with respect to that line, and all the energy is in form of kinetic energy. What about here? Here we are going to have potential energy. Well, looks like it's halfway. So that means potential energy has to be 2 joules, because potential energy depends on the height. It depends on the height. And kinetic energy here, to make sure that the sum has to be 4, it has to be 2 joules here. Likewise, the situation here will be the same as the situation at this point here. All right, so this is the energy conservation with respect to the pendulum. So this is a pendulum. We are discussing this with respect to the pendulum. All right, so now let's look back and say, why did we ignore friction and air resistance? Why did we say let's ignore, and this is the case? Well, again, I think this is the right time to talk about this. If we take friction and air resistance into account, some of the energy will be transformed into other forms of energy that we haven't discussed yet. For example, here, if I were to take air resistance into account, by the time I see the ball here, around here, we may not have all the potential energy converted to kinetic energy. Some of the energy might be converted into other forms of energy, such as thermal energy or sound energy, right? And for that reason, the energy here might be maybe less. It might be, for example, 18 joules. Now, this means that there's a missing part of the energy, and that missing part has to be accounted for. It has to be accounted for, because we are going to have 18 plus 0, which is 18, and that will not be equal to the 20 joules we are looking for. So that means there is a missing part, which is 2 joules, and this can be accounted for other forms of energy. Other forms of energy. And these other forms of energy can be can include thermal energy or sound energy. Thermal energy, let's use heat energy. Heat energy or sound energy. As the ball is falling, there's some sound energy. All right, these are the forms of energy. But the funny thing is, if we account for those missing parts, the total energy has to always equal to 20 joules. Let's look at this example. If we were to say that, oh, there is some friction on the plane surface, maybe there is some friction, for example, and the air resistance is there. As the masses are actually falling, they experience some air resistance in these positions. So this is the rest position and this is the final position. But as they are moving, there is some air resistance, right? I'm trying to draw air resistance actually. Now that air resistance plus the surface friction are going to actually reduce some of the speed of the ball at each and every point compared to what it was supposed to be when there was no friction. In the end, we are going to see that by the time the crate has fallen to this level here, we are going to have a different situation. This kinetic energy might not be exactly 1000. It might be, for example, maybe 950 joules. Now when you try to find the sum of potential energy and kinetic energy, you may end up with just 950, and then you wonder what's going on. I thought maybe the sum has to be the same in a system always. The reason here is that some of the energy, which we can say that is the missing part of energy in this case, looks like is 50. Some of the energy, the 50 joules, has been converted to other forms of energy. And that could include thermal energy or heat energy or sound energy as the crate is falling down. So what we are saying is that in general, whatever we do, we see that the total energy of the system in a system never changes. So this is summarized in one of the ideas in physics, one of the principles of physics, which is called conservation of energy. The principle of conservation of energy says that the energy that we see, the energy that we know, energy cannot be created or destroyed, but it can be transformed from one form to another. So I'll just briefly write here that the total amount of energy in a system never changes. It never changes. So this is the principle of conservation of energy. The total amount of it never changes. Of course, we saw that there can be some transformations from one form of energy to another, from potential energy to kinetic energy to thermal energy, or maybe sound energy. Those are some of the energy transformations. But if we look at the total score, the total amount of energy, it remains the same in any system and cannot be created or destroyed. That's what people say, energy cannot be created or destroyed. And therefore, it has to remain the same. At this point, we're going to see two examples to see how we can apply the conservation of energy. Example one relates to a ball here that drops to bottom ground somewhere here. This is my usual ground. I hope by now you know how I draw my ground and you know how I draw the balls. Just circle, okay, to save time. And we are told that the falling distance here is actually 10 meters. 10 meters is the falling distance. And we are told that ball starts from rest. Ball starts from rest. That's what we are told. And one thing that we are also told, well, ball starts from rest. Yeah, 10. This information is enough. This information is tough. So the question here is, what is the striking velocity? Striking velocity is the velocity just before the ball strikes the ground. Striking velocity just before the velocity, just before the ball touches the ground. So what will be the striking velocity? We are going to use the principle of conservation of energy to solve this problem. Let me use a different color. I'm going to use red. So to solve the problem, I'm going to use this space here. I hope it will be enough. I'm going to use this space. So the way you start this problem is to say the total energy, which we call total mechanical energy, at position 1 must be equal to the total energy at position 2. So what I'm trying to say here is that potential energy at position 1 plus kinetic energy at position 1, this is the total energy. According to the conservation of energy, it must be equal to potential energy at position 2 plus kinetic energy at position 2. So this, what I have written here, is a mathematical equation for conservation of energy. Now I can write potential energy at 1 as just mg times height 1, and then plus kinetic energy at position 1 is just half. I forgot the half. Remember, kinetic energy is half something. So it's 1/2 m initial velocity squared. The answer must be mg height at position 2 plus 1/2 mv. This will be velocity at position 2 squared. That will be the striking velocity. Actually, the v2 is a striking velocity. Now I realize that the ball starts from rest, so this component goes to 0. And I realize that height 2, or height at position 2, is 0. There's no height at position 2 right here because the ball is on the ground at a reference line. So this goes to 0. So I end up with a nice formula that says mgh1 is equal to 1/2 mv2 squared. Now I can multiply both sides by 2. Then I'll end up with the following. Twice by the way, I can cancel the mass. This mass and this mass cancels out because they are available on both sides of the equation. Then 2gh1 must be equal to v at position 2 squared. So this is a nice formula that will help me to find the value of v2. If I find v2 from there by taking the square root of both sides of this equation here, the square root of v squared 2, this part, is just v2. Then the other side, the square root looks like 2g times h1. Then I can plug in the given values. I'll plug in 2 times g, I'm going to use a 10 meters per second squared. Then times height 1. The height 1 at position 1 is 10 meters, 10 meters. So that should give me square root of 200 something. And for the sake of space, I'll just give you the answer. V2 will be square root of 200. Square root of 200 will be 14.1. 14.1 meters per second. So this is the velocity at position 2, which is the striking velocity of the ball. Let's look at example 2, and that will be our last example in this lesson. Example number 2. Example number 2, we have a situation whereby we have a cliff. This is a cliff. This is a cliff, and you toss a ball at a certain velocity, and the velocity is given for you. This velocity is 6 meters per second. We can call that initial velocity, and then the ball goes down like that to a certain position. The ground is here. That's my ground. Well, let me draw a nice ground. Let me draw nice ground. Okay, straight lines are always beautiful. Okay, all right. And now let me put this to indicate that it's the ground as usual. So the ball now tossed it from there. Now its ball will be here. The question is the same. What will be striking velocity? In other words, what will be the velocity of the ball just before it strikes the ground? One thing that is given also is the height of the cliff. The height of the cliff is given as 10 meters also. So basically this problem is similar to the previous one. We had also 10 meters, remember? We had also 10 meters as the height. The only difference here is that we are giving the ball velocity from the beginning. At first, we had the ball start from rest. In this next problem, the ball has some velocity as it begins to move down. Now we are going to do the same. I'm going to use a different color to solve this problem. The way we start solving the problem is to realize that the potential energy at position 1 plus, well, this is position 1 here, and this is position 2. The potential energy at position 1 plus the kinetic energy at position 1, it must be the same as the potential energy at position 2 plus potential energy, plus kinetic energy at position 2, right? Then you write 1/2 mv1 squared plus, I'm so sorry, the potential energy is mgh1, mgh height 1 plus 1/2 mv velocity at position 1 squared equal to potential energy at position 2 will be mgh2 plus kinetic energy. Can you guess? 1/2 mass times velocity, but at position 2 squared. We can cancel out the mass. As you can see, the mass can cancel out. This mass cancels out, this mass cancels out, cancels out, cancels out. And we can also understand that at position 2, the height is 0. Actually, the whole thing here goes to 0 because there's no potential energy at that point, or there's no height because our reference line starts from there. Therefore, H2 is 0. The whole thing here goes to 0. So what we are remaining with is the following. We are remaining with GH1 plus V1 squared over 2 equal to V2 squared over 2 as as what is remaining. If I multiply by 2 both sides of this equation, I'll end up with the twice GH1 plus the next expression. If I multiply by 2, the 2 goes out, so I'll remain with V1 squared equal to the last expression. I'll only have V position 2 squared because the 2 there will cancel. So I have changed the formula into this formula. And finally, I'm looking for V2. So I'll take the square root of both sides of this equation, square root of both sides of that equation. So that will give me square root of 2GH1 plus V1 squared will be equal to velocity 2, which is the striking velocity. Then I can substitute the numbers. I will keep the units. Let me so let me say the square root of 2G, I'll take it as 10 without the units. I just want to save time here. H1, that's the height, was 10 meters. Then plus velocity, initial velocity 6 squared. That is V1 squared. Now this should give you about 5.4 meters per second. So this will be the striking velocity this time around. All right. So I would like you to try a similar problem by starting with the V initial, V1 equal to I want to increase the speed and see what will be the effect of increasing speed on the striking velocity. So let's assume the V1 is no longer 6 meters per second, but V1 is equal to, let's make it like 20 meters per second. Or let's double it, just double it, 12 meters per second. If V1 is that, what will be the striking velocity? Find V2. Find V2. So this is your problem for you to think about and see what will be the striking velocity. One thing you should remember is that we ignored air resistance and friction in this problem and the previous problem, this one. So usually we do ignore those, and for practical purposes, we usually get close answers. Air resistance doesn't affect that much objects of the size of like a ball, you know. If a ball is massive enough, air resistance can be practically ignored. I mean, we can ignore that, and our answers are very close to what we could find if we considered air resistance. Anyway, I will stop here, but we are able to solve these problems because of the conservation of energy. Thanks to the conservation of energy, the principle of conservation of energy has enabled us to solve very crucial problems. Energy in a system remains the same, never changes. It can transform from one form to another, but the total energy remains the same. I'll stop here. If you have questions, please let me know. Bye for now.